G'day pilots, Captain Mulch here for Oz Aviator. Today we're here in the Oz Aviator hangar with the mighty beach skipper. More of this later. Today we're going to be doing basic aeronautical knowledge, power plants and systems, part 1. Stay tuned. G'day everyone, I'm Captain Mulch and welcome to Oz Aviator. I'm an Australian GA and RA Oz flight instructor, and this is the second of the Oz Aviator ground school lessons. The lessons are based on the Australian Civil Aviation Safety Authority Manual of Standards, and in this series each session will cover a section of the Manual of Standards, and it'll be covered in sequence. I strongly encourage you to do further online learning. There's plenty of good material out there, and make use of any books that you can get your hands on. Today's book recommended is Mechanics of Flight by Commode. You can buy that online, and I have seen it available for download. I'm not sure how legal it is, but you can get it as a PDF, and it's the 11th edition there. Okay, let's get into the slides. So today is still basic aeronautical knowledge, BAK, power plants and systems, part 1. I've broken this up into 2 parts because there's quite a bit of material to cover. So this first section will be part 1 of power plants and systems. So as an introduction, this presentation will cover the operations of a 4-stroke internal combustion engine and its components, the effect of altitude and temperature on engine performance, and the function of various engine components and systems. So first of all, let's have a look at the 4-stroke internal combustion engine and how it works. First of all, have a look at some of the components. There's the crankshaft at the bottom, which is doing the turning, connecting rod, which connects the piston to the crankshaft. The piston has piston rings, which enable the piston to fit tightly into the cylinder. So the cylinder is what the piston moves inside. The space within the cylinder is called the combustion chamber. We have intake and exhaust valves, spark plug at the top. Now the reason it's called a 4-stroke engine is because each time the piston moves up or down, it's counted as 1 stroke. So the first stroke, which is the intake stroke, the piston moves down, the intake valve is open, and an air-fuel mixture from the carburetor enters the combustion chamber. The next stroke is the compression stroke. The compression stroke compresses the air-fuel mixture, which is in the combustion chamber. Note both of the valves are closed as the compression occurs. The spark plug fires, which ignites the air-fuel mixture. Now, just note, for further on in this presentation, we'll be talking about impulse coupling. And just on the note here, the spark plug doesn't fire when the piston is at the top of the cylinder on the compression stroke. It fires just before the piston reaches the top of the compression stroke here. Third stroke, power stroke. So the spark plug has ignited the air-fuel mixture within the combustion chamber. This forces the piston down, providing power. And then the 4th stroke, the exhaust stroke. The piston moves upwards, the exhaust valve opens, and the exhaust gases, those burnt gases, are then forced out of the cylinder. And then back to the first stroke again. So that's the basic operation of a 4-stroke internal combustion engine. Okay, looking at some of the engine components in more detail here. So here we have the crankshaft of the engine, which is doing the turning. The crankshaft is connected to a camshaft via timing gears. The camshaft has bits of lobed metal on it called cams, which rotate and push the push rods, which then activate the intake or exhaust valves of the engine. Now this all happens in, it's timed by the timing gears so that the intake and exhaust valves open and close correctly. Over here there's a graphic of a horizontally opposed aircraft engine. Reason it's called horizontally opposed is the cylinders are horizontal and opposite each other. You can see the cylinders here. Inside is a piston, conrod connecting to the crankshaft of the engine, which rotates the propeller. And here's a cutaway of a typical horizontally opposed aircraft engine. Carburetor at the bottom, providing an air-fuel mixture to the intake manifold. That air-fuel mixture comes in, the valves are on top of the cylinder here. The intake valve opens, allows the air-fuel mixture in. Here's the piston ring, connecting rod here connecting the piston to the crank. Notice also the exhaust manifold here. So when the exhaust valve here opens to allow those burnt gases out of the engine, that exhaust then comes out the exhaust manifolds here. Also note the spark plug leads and spark plugs, dual ignition, so there's two spark plugs on each cylinder, top and bottom. Your bottom spark plug with spark plug lead and top spark plug with spark plug lead. Another thing to note is when the piston reaches the top of its travel inside the cylinder, the top of that travel is called the top dead center. The bottom of that travel is called bottom dead center. Okay, the effect of increasing altitude and temperature on aircraft performance. Now with the atmosphere, air density decreases with altitude and it decreases with temperature. So the efficiency of the engine will decrease with a decrease in air density. So the higher you go in the atmosphere or the higher the temperature, your aircraft will not perform as well as it would lower in the atmosphere and at a lower air temperature. There's an example here. So we're at Ballina, more or less sea level, and it's a 15-degree day. The aircraft will take off in 830 feet. But if you're at Mount Hotham, which is Australia's highest airfield, and it's a 40-degree day, and there's a pressure altitude there of 5,000 feet, it will take 1,570 feet, almost double the amount of distance for the aircraft to take off. And that's due to the power being produced by the engine has decreased because of the decrease in the air density due to altitude and or temperature. A throttle lever and RPM gauge. So the throttle lever here, which is the black one on a throttle quadrant as it's called, you push the throttle lever forward, the engine produces more power. You pull the throttle lever backwards, the engine produces less power. There's an in-out style throttle control here, which usually found on Cessnas and other aircraft. Works the same way. Push it forward, the aircraft engine produces more power. Pull it rearwards, the aircraft engine produces less power. The gauge on your instrument panel that shows the amount of power being produced by the engine is your RPM gauge. Note here it says RPM hundreds. So if the needle here is pointing to 20, it's 2000 RPM, pointing to 25, 2500 RPM. So it's an indication of the amount of power being produced by the engine. Carburetor and throttle. So your throttle lever is connected to the carburetor via linkages, and the throttle lever controls your throttle valve. It allows more air and fuel mixture into the engine or less fuel and air mixture into the engine. So let's have a look at how the carburetor works and its components. So here's your fuel line with your fuel coming into the float chamber. Now the float chamber is like a small reserve, a buffer of fuel inside the carburetor. There's a float in there that allows fuel in as the level in the float chamber decreases. There's a mixture needle. Mixture needle is connected to your mixture control, which is inside the aircraft, usually next to the throttle control. The mixture needle varies the amount of fuel that goes to the discharge nozzle of the carburetor. So your air enters the carburetor, and there's a constriction within the carburetor called the venturi, and it creates an area of low pressure. And that area, because of the low pressure there, the fuel is sucked through the discharge nozzle in a fine spray, which then allows the air and fuel to mix, creating an air-fuel mixture. The throttle valve, as we said, connected to your throttle lever. If the throttle valve is open, as shown here, it allows more air and fuel in, and the speed of the engine will increase. If you close that throttle valve, it allows less air and fuel mixture in, which will cause a decrease in engine RPM. Magneto and dual ignition. So the magneto is separate from the rest of the aircraft electrical system, and it provides power to the spark plugs so that they can provide spark to ignite the air-fuel mixture inside the cylinders of the aircraft, inside the combustion chamber. The reason for being two magnetos is because that's redundancy. If there's a problem with one of the magnetos, the other one will enable the aircraft to still operate, the aircraft engine to still operate. A second reason for it is with two spark plugs, the air-fuel mixture inside the combustion chamber of the engine burns better with two sparks. So the way a magneto works, it's similar to a generator. There's a magnet that's spinning. The aircraft engine drives the magneto, so the magnet's spinning. There's a coil in there, which then picks up that magnetism from the spinning magnet, creates electrical charge, and that electrical charge is then distributed through to each of your spark plugs in the engine. Now note here there's also impulse coupling. We'll have a look at what the impulse coupling does in a minute or so, but there is usually only one impulse coupling on one of the magnetos off the left magneto. And like I said, we'll look at that in a minute. Now, you have a magneto switch on the aircraft, which is also used to start the aircraft. Once the engine's started, you move the magneto switch to both position. To test that both magnetos are operating correctly, as one of your aircraft run-up checks, you'll move the magneto switch to left and then to right, and it's an indication that both magnetos are functioning correctly. Once you've tested them, you move it back to both, obviously. Alternator. Now, once the aircraft engine is running, there's a belt that attaches the alternator to the engine, and the alternator spins and provides electrical power to the electrical systems of the aircraft. The way it works, there's an electromagnet on the inside of the alternator called a rotor. It spins, creating a rotating magnetic field, which is picked up in the stator. The way an alternator works is it actually produces alternating current, which is why it's called an alternator. And the alternating current is a backwards and forwards current. The electrical system of the aircraft uses direct current, a current that only moves in one direction. So there's a series of diodes, also called rectifiers, which rectifies the current to move in only one direction. Now, varying your engine speed can lead to a variation in the amount of power produced by the alternator. To guard against this, there's a voltage regulator, which is a box of magic tricks. It monitors the amount of power being produced by the alternator. If the RPM of the engine decreases, some more current to the rotor and increases the amount of power being produced by the alternator. And this is what's called a voltage regulator. It sits there and monitors the amount of power being produced by the alternator. The voltage regulators are usually mounted on the firewall of your engine compartment or under the instrument panel of the aircraft. This is a Cessna style voltage regulator. So an alternator and voltage regulator go hand in providing power to the aircraft electrical system. Battery. It's a device that converts chemical energy into electrical energy, so it's a store there in the aircraft to provide power. One of the functions of the battery is to provide pre-flight power, so before the engine starts operating, if you're, say, lowering your flaps to do a pre-flight check or checking a stall warning horn, if you have an electrical stall warning horn, you can turn your power master switch on, lower your flaps, check your stall warning horn. The battery's providing that power. It also provides power for starting the engine. So when you start the engine, the battery power is used to start the engine. There's two main types of chemistries that are used in aircraft engine batteries. One is nickel-cadmium, NiCad, and the other is a lead-acid battery. One of the other functions of the battery, if there's an in-flight failure of the alternator, which is indicated there's an alternator light if the alternator does fail, or maybe it's starting to fail and it's not operating correctly, the battery will then provide power to your electrical systems in the aircraft. The battery also acts as a buffer. One of its other uses is acting as a buffer to regulate the electrical system. So it regulates the voltage in your electrical system and ensures that there's an acceptable quality and quantity of power provided to the equipment that require the power. Now, because the battery, it's a chemical reaction that's going on there in your battery, and that chemical reaction can produce fumes. Often batteries have a ventilating system, which consists of an air intake, which provides a positive pressure into the battery compartment here, where your battery's stored, and then the air comes out the other end to remove any of those gases. Ventilating system provides ventilation to the battery compartment to remove any of those gases that may build up in there. Propeller. So the propeller is what converts the rotary power of the engine into thrust. The propeller attaches to the drive shaft either directly, as in Lycoming and Continental engines, or through reduction gearing, as in the, say if you're flying a Diamond with the Austro Turbo diesel, or a Rotax 582, the engine runs at a higher RPM than is required for the propeller, and there's a reduction gearing. There's a gearbox there which reduces the RPM to the correct RPM for the propeller. Propellers can be made from wood, which is the original propellers were all made from wood. They can be made from metals such as aluminium, or composite material, which is a new style of propeller. Now note here on the propeller, the cross-section of the propeller blade. You can see the cross-section that looks similar to an aircraft wing. And that's because the propeller acts similar to an aircraft wing to provide thrust. As the propeller spins, air flows over the propeller and it provides a forward force on the propeller to pull the aircraft through the air, similar to a wing producing lift. Now, because of this, the propeller rotates at a slower speed at the hub than it does out of the tips here. So to compensate for that, there's what's called blade twist. The blade twist ensures that there's a constant thrust on the propeller from the root of the propeller to the tip of the propeller. Some propeller terminology. So if you draw an imaginary line from the leading edge to the trailing edge of the propeller here through the cross section, that is called the chord line. The pitch or blade angle of the propeller is the angle at which the propeller is presented to the rotational direction of the propeller. The angle of attack is the angle between the chord line and the relative wind. So this relative wind changes if the aircraft is sitting on the ground not moving but the propeller's spinning. The angle of attack is greater than if the aircraft's moving, because that relative wind of the aircraft moving through the air changes and the angle of attack decreases. There's three propeller types. There's fixed pitch. So in your Cessna 152, you can't change the pitch or blade angle of the propeller. It's fixed. There's a constant speed propeller, where you can change the pitch or blade angle of the propeller. And there's a mechanism in there that controls the change of that pitch or blade angle to maintain the propeller spinning at a constant speed. There's also ground adjustable propellers. They're not very common, but the reason for them is you may have an aircraft that you're just doing circuits with. So lots of climbing, requiring the propeller to act more efficiently in a climb. So you'd have the pitch or the blade angle of the propeller at a finer pitch. But then you may be taking the aircraft out on a navigation exercise, doing a cross-country navigation exercise, where you want the propeller to be more efficient at a higher speed, and you can adjust the angle of the propeller blade to be more efficient at a higher speed, and that's a ground adjustable propeller. Okay, circuit breakers, fuses and bus bars. Now the electrical system of your aircraft has got different circuits inside there providing power to different pieces of equipment. And those circuits may have a problem such as a short circuit or some kind of malfunction that could lead to the wire in that circuit melting or damage to electrical equipment. So circuit breakers and fuses can detect that increase in that malfunction if there's an increase in power within the circuit that could melt the wires or damage equipment. And the circuit breakers and or fuse will cause a break in the circuit to remove the power from that circuit. The way a circuit breaker works is it's got, in the back of it here, it has a switch in there that can sense the temperature in the circuit. If the temperature in the circuit reaches a certain amount, the circuit breaker will pop and open the circuit. Similarly, the fuse has a fusible link in here, either a thin wire one or a flat one, similar to that illustration. And what happens if the temperature in the fuse reaches a certain amount? The fusible link will melt, thereby removing the power from the circuit and preventing further damage. Now, a bus bar, or a bus as it's referred to, is just a common electrical link for components in your aircraft electrical system. Often there's two buses, the main bus and an avionics bus. And the reason these are separated is because when you're starting your engine, there may be a spike in the electrical system that could damage delicate instruments, such as your radio. So there's a switch that is off for the avionics bus, avionics master switch. Once the engine's started and the aircraft's up and running, you then flick the avionics master switch on, and that provides power to the avionics bus, which then enables you to turn on your radios, transponder, etc. Okay, impulse coupling. Now we mentioned the impulse coupling previously when we were looking at the magnetos. And as I said before, there's only one impulse coupling, often on your left magneto. Now there's two reasons for the impulse coupling. One reason is to retard the spark when the aircraft's starting, when the aircraft engine is starting. When the piston is reaching top dead center on the compression stroke, when the aircraft's normally running, the spark occurs before top dead center. Now what happens on starting the aircraft if the spark occurs before top dead center? The aircraft engine could start rotating in the wrong direction. So the impulse coupling retards the spark, so it holds the spark back until after the piston has reached top dead center, and then the spark plug fires, producing power for the engine, burning the air-fuel mixture, and it prevents that scenario of the aircraft engine starting in the wrong direction. The other thing is, when you're starting the engine, there may not be quite enough power to get the spark plugs operating efficiently. So inside the impulse coupling is a spring, and the spring holds the magneto back for a short period and then releases the power from that spring, makes the magneto spin faster and produces a stronger spark to start the engine. Oil cooler. So the oil cooler in your engine lubrication system cools the oil as it flows around the various components of the engine. So it acts similar to a car radiator in that the oil flows through the oil cooler and air flows over the top of it to cool the oil. You can see in the diagram here, dialyzed engine, you have your sump, which is where the oil is held. The oil pump pumps the oil out of the sump through a filter and through your oil cooler, thereby cooling the oil. And attached to the lubrication system is a oil temperature and pressure gauge, which gives an indication of the temperature of your oil, so you can tell whether it's operating within the correct operating temperature. It also shows you the pressure of the oil to make sure that the pressure of the oil within the system is at the correct pressure. Once the oil's been cooled, it then moves back into the engine. So the oil in your aircraft lubrication system not only lubricates the aircraft engine, but also helps to cool the engine by cooling the oil and helping to cool the engine down. Fuel tank vents. So fuel tank vents are designed to provide a slight positive pressure to your fuel tank during flight. One of the main reasons is to prevent fuel siphoning off, because the way aircraft wings operate is that there is an area of low pressure over the top of the wing which could lead to fuel siphoning. So the fuel tank vents are there to help prevent that occurring. Also, as the fuel is sucked from your fuel tank into your engine, air is required to replace that space within the fuel tank. Another reason is letting air out during refueling. So as you're putting fuel into a fuel tank during fueling operations, the fuel tank vent will allow air to escape out of the fuel tank. It also allows, as your aircraft goes higher or lower in the atmosphere, the air pressure changes, and the fuel tank vent will allow air in and out of the fuel tank to compensate for that change in air pressure. One last reason also is on a hot day, especially if you've really filled your fuel tanks up high, as the temperature increases, your fuel will expand and it needs somewhere to be able to get out of the fuel tank, and the fuel tank vent will allow some overflow. Okay, in conclusion, that's the end of part one of power plants and systems. So this presentation covered the operation of the four-stroke internal combustion engine and its components, the effect of altitude and temperature on engine performance, and the function of various engine components and systems. Okay, thanks everyone for watching this session of Oz Aviator. Any questions, suggestions, please in the comment section below. Don't forget to press like and subscribe, and stay tuned for more content. Until then, keep your wings level.